So I thought I'd just take a break from my skiing to give some hints to those of you who are having trouble with your homework for over the holidays. So we're on these questions starting from question 6, which is on page 38. So the first bit of that question is just some facts you've got to look up. No excuses for that, the facts are in the booklet, you have to find them. The next part, calculate the decay constant. Well, I'll tell you what answer you're trying to get. You're trying to get 4.6 times 10 to the minus 4 per second. If you get 4.5 times 10 to the minus 4, you've probably missed out a stage. There's something you've forgotten about in the data that you've got to do before you can start using those numbers. The number of radioactive nuclei you've got to find, my answer is 2.3 times 10 to the 5. And while you don't need to worry about it for this question, if you think about how you're always told there are millions and millions and millions of atoms in anything, to have 230,000 atoms is really a tiny number for atoms. It doesn't come into this question because the thing to remember is that radioactive materials will probably contain all sorts of isotopes, and there might just be a tiny, tiny fraction of the atoms there that are actually of the radioactive isotope. So if you're wondering why you got such a small number, that's probably the reason. Right, question 7. I think that's all stuff that you can look up. Nothing too tricky there. Apart from the last bit, what must be done to validate the predictions of an unconfirmed scientific theory? That question's got absolutely nothing to do with radioactivity. That's testing your knowledge of sort of science in action. So thinking sort of general terms, what would you do? Okay, on to page 8. Well, it starts with asking you to explain random nature. And if you look on page 35, you'll see some explanations there. But just make sure that when you write your answer, you don't use the expression back in day. Next part of question 8 is plotting a graph on the axes. And although it says sketch a graph, just because it calls it sketch, that doesn't mean you should sort of deliberately do it roughly. You should have enough information to be able to plot a few points, maybe 3 or 4 points, so you can do a reasonably neat graph through those points. 8 part C, trying to calculate the decay constant, and the answer you should end up with, if you're doing it right, is 8.5 times 10 to the minus 9 per second. And then the next bit, 8 part C, the second bit of that, the number of atoms, I got 6.5 times 10 to the 13, so hopefully you'll get the same. And then the answer you should be looking for the last bit of question 8, I got 3.4 times 10 to the 7 seconds. Okay, question 9. Well, that's just the first part, completing the equation. You just got keeping track of particles, so you should be able to do that. When it comes on to working out that distance, how close does the alpha have to get before the reaction is going to occur? The answer I got, so it's the one that you should be getting, was 2.7 times 10 to the minus 15 metres. Right, over the page, question 10. Now, part of this is using that grid. When you did the last lot of homework, some people seem to have difficulty with that. You've got to remember that if the proton number and the neutron number are both changing, the lines you draw on the grid would be diagonal, wouldn't they? Not horizontal or vertical. Right, question 11, the one about the carbon dating. Now, I did put a section in the booklet explaining about carbon dating. This question sort of takes you through the ideas of it, so even if you hadn't heard of it as a technique, there's enough information here in using the equations to be able to work out the age of the boat. So 11 part A, what's meant by decay constant? Well, that's something to look up. There's enough explanation of that in the booklet, so no excuse for leaving that blank. The half-life of carbon-14, the answer I get, well, the actual answer I got was 5,730 years. It says giving it appropriate number of significant figures. And this is one of the things where I disagree with the mark scheme, because the mark scheme says 5,730, but I reckon the right number of significant figures is only 3. And the only way you can write 5,730 only using 3 significant figures is to put 5.73 times 10 to the 3. The next bit, to show that the rate of decay is 1.15 becquerels. Well, another name for rate of decay is activity. And you've got an equation for activity if you know the decay constant and you know the number of atoms. So you have a look at the number of atoms, and you've got to be very careful there, because of course when it says the number of atoms, it means the number of carbon-14 atoms. And most of wood doesn't contain carbon-14, but the question does tell you how much of the carbon in wood is carbon-14. So you've got to do a little bit of working out for yourself there. The actual age of the boat, I get that to be 4,720 years. But again, significant figures, I actually put it as 4.72 times 10 to the 3. And it's probably worth doing like a common sense check there. If you look at the activity, if new carbon has got an activity of 1.15 becquerels and this old carbon is 0.65, hopefully you spot that the activity has not quite gone down by half. So when you get an answer and the age is just less than the half-life, that's probably a good sign that you've got the right answer. Okay, question 12. That's got calculations in there. And the first one is a sure one. So, as long as you can work out what's the area of a sphere, you imagine that this radioactive source is sending out gamma rays in all directions. So if you imagine 2 meters away, which is where the scientist is, by the time the gamma rays have gone 2 meters, they'll have spread themselves out over an area that's like a sphere of radius 2 meters. So if you work out what is the area of a sphere of radius 2 meters, that's the area that all these gamma photons are spread out over. So you can use that to work out how many there would be per square centimetre. And then for the last bit, it's just like we've had equations for n, and we said you could use A or you could use C in that exponential equation. You could also use intensity. So you could use I equals I naught e to the minus lambda t and get an answer for the new intensity. Right, anyway, better go back to the slopes now. See ya.